Hey guys, I want to talk to you a little bit about magnets today. Some interesting stuff happens here. You're looking at a picture of a bar magnet right there. There's a north pole and a south pole marked on that. And these lines are what happens when you shake a little bit of iron filings on top of a magnet, or even better, put the magnet on a table, put a piece of paper on top of that, and shake your iron filings on there. The iron filings are ferromagnetic, so they are attracted to a magnet like a nail would be or something, and they will actually line up with what we call the magnetic field. And this is probably the best way to see that and to visualize what's going on. We'll talk about all that in just a second here. First of all, let me remind you that there are two kinds of magnets. That one of these is called a permanent magnet, and a permanent magnet right here would be any kind of material that holds that magnetic field, that attracts iron filings, nails, paper clips, whatever. And you can stick it to your refrigerator and you come back the next morning and it's still stuck on there because it's a permanent magnet. Over here, on the other hand, we have what's called an electromagnet. And what you should know here at the beginning of this game is that moving charge generates a magnetic field. I have moving charge when I take a battery and I hook a wire up and I run that wire. If you run it around a nail in a loop like you see here and back, see how there's a complete circuit there? That's moving charge. It's a current. So that's going to generate a magnetic field. And right there looks like they're picking up some paper clips or something. And in the same way that a permanent magnet will. The instant I take the wire off of the battery, though, it stops being a magnet. I no longer have moving charge. So there's no longer a magnetic field there. And all those staples would just fall back into the cup. Now, you could say, I don't see any moving charge over here, but if you could zoom in on each atom of that permanent magnet, you would see electrons orbiting the nucleus. And those electrons are charges, they are moving charges, therefore they're going to generate a magnetic field. And in the end, that's the origin of that magnetic property over there, even of the permanent magnet. So both of these kind of have the same thing going on. There's moving charge generates a magnetic field, and then we can pick up some stuff or hold our kids' artwork on the refrigerator, whatever. All right. Here's a picture of a material that is unmagnetized at the top. If you just go out into the shop and get a nail, it's not going to be a magnet. You can make it a magnet, but at the moment, each of those little atoms, each one has its own magnetic moment. That it's like each one is a little magnet, but one's pointing kind of southwest and one's pointing northeast, and those are going to cancel out. And this one that points up and that one that points down, and this one to the left and that one to the right. The net effect is zero. They all cancel out. If I could get them to line up a little bit, then I'd have a weak magnet. But if I could get them to line up all pointing in the same direction, like horses pulling in the same direction, I'd have a really strong magnet. And so that's what we want to do. You could take a nail and you could put it in a magnetic field and leave it there, and the atoms would align. They would turn so that their magnetic moments align with the magnetic field. If you heat it up, they are even more free to orient themselves with this external magnetic field, and then when it cools off, they're locked in that form. So lots of applications of magnets. But you probably know that if you break a permanent magnet, you end up with two permanent magnets. Each of those will have a north pole and a south pole. And of course, the north pole of a magnet is attracted to the south pole of a second magnet. Or if I were to turn either one of those pieces around, then a north and a north would repel. They would push away from each other, just like a south and a south would. Opposites attract, and like poles repel each other. All right. There's some different materials here. You don't have to know a whole lot about this. Don't feel like this is going to be on the test or something. But in just thinking about the different kinds of materials and why plastic is never magnetized, it will never stick to your refrigerator, and the magnet won't stick to it, and why a nail will stick to a magnet, then this is a little bit of that information right there. It's but not really what we're trying to do. Diamagnetism, there's no net magnetic moment. Maybe the shells of your electron clouds are filled. So you've got one electron orbiting left and one right, right? That's going to cancel out and I don't get a net magnetic moment. Or maybe there's no unpaired electrons. If I, in an outer shell, if I had one that was orbiting, but it didn't have one that was canceling out, then, I would, I wouldn't, if I had an unpaired electron, I could get a magnetic moment. But if they're paired, then so that goes back to chemistry and the setup of electron clouds. Paramagnetism, you got weak net magnetic moments. You've got some unpaired electrons in there. This is the strong one, the ferromagnetic, strong parallel magnetic properties. We're talking about iron, cobalt, nickel, some rare earth stuff, neodymium makes super strong magnets. Those little silver disc magnets that you see, those are something like neodymium or other ceramics that people cook up and mix different weird stuff together to get stronger magnets. You got two down here, ferromagnetism and antiferromagnetism. Both refer kind of to when a material breaks up into little regions. And these regions may be locally oriented, but not globally. So more or less, these are pointing up, but that one south to north kind of weakens it, or maybe you've got a downward area, sublattice moments and stuff like that. Um, that's not quite as important, but you can kind of get a feel for that. Let me tell you about field lines real quick. On test 2, we talked about the electric field, and we saw that if I had a positive charge and put a small positive test charge there, it would be repelled from that, and I could draw an arrow that would represent the electric field. If I had a positive and a negative charge, this guy would be repelled by the positive charge and attracted over here to the negative charge. And we mapped all those lines and talked about the electric field. Well, this is the same thing. It's the magnetic field. So if I put a magnet down on a table and I start putting not small positive test charges, but little compasses there. A compass is a little bitty magnet, right? And so if I put some little bitty magnets or little bitty compasses down there, you see how they line up? That maps the magnetic field lines. Right here, this compass has a north pole and a south pole. The north pole is repelled by this north pole, and it's simultaneously attracted to the south pole over here. This south pole is attracted to the north pole, so it's trying to get over here. The north pole is trying to get away from it. And as I move those compasses or put different compasses down, I will see the direction of the magnetic field at each point in space. And you remember that's what a vector field is. When you've got every point in space has a vector associated with it that gives the magnitude and the direction of the field line. So this would be the direction at least. You got to multiply some numbers to see what the number is of the magnitude is. But we'll talk about that in just a second. They're very similar here, electric fields and magnetic fields. So that's handy. How do we measure magnetic fields and what's the unit of them? Well, we measure in Tesla. The Tesla is the unit of magnetic field that we like the best. It comes back to 1 Newton per amp meter. So these are all metric units. We feel comfortable with these, and since we can calculate Tesla out of nice standard SI units, then metric units, we prefer that. There are some other choices, Weber per meter squared and Gauss. This right here would serve as the conversion factor to get back and forth between all of those. If you wanted to go from Gauss to Weber per meter squared, there's the conversion factor. Just use those two parts. Okay, but just about everything we do in here will be Tesla. And how much is a Tesla? Well, a strong permanent magnet's about 1/10 of a Tesla. If you go to the junkyard and look at their electromagnet that they use to pick up a car and drop it in the crusher, that's about 1 Tesla. Okay, so a 1 Tesla magnet is a pretty strong magnet. The Earth is a magnet. Right here, The Earth has a magnetic field due to currents of molten material in the core. We live on the crust of the Earth. Inside that, you got the mantle. Inside that is a liquid core where hot magma is circulating in convection currents, like we talked about in test one. Um, that molten magma, lava, if it comes up on the surface of the Earth, surrounds the, the metallic core, the solid core of the Earth. Anyway, that magma moving in circles, that's moving charge, it's highly charged material. So you're going to get magnetic field lines off of that. And you can see here the magnitude of it. It's not very strong, 3 times 10 to the negative fifth Tesla, right? But it's enough to hold a compass here in South Carolina and say, the magnetic pole of the Earth is that way. But there is an interesting thing to think about here. See how the North Pole of my compass points to what we call the North Pole of the Earth? Shouldn't the North Pole of a compass be attracted to the South magnetic pole? So at the moment, the magnet of the Earth here is kind of upside down. The North Pole, what we call the North Pole, is actually a South magnetic pole and vice versa down here. In times past, the magnetic field of the Earth reversed, and it used to do it on a fairly regular basis. It hasn't done it for a long time. Some people think that we're due for a magnetic pole reversal. That would make things very interesting, but who knows? We'll see. Look that up if you're interested in it. Magnetic pole reversal, and read about the effects. If this virus isn't scary enough for you, that would be something else to worry about. Okay. Anyway, I need to talk to you about the right-hand rule. There are a lot of places in magnetism where we have to multiply vectors. And you remember that there's 3 ways to multiply vectors. One's called the scalar product and one's called the dot product. In this field, we tend to use the cross product. And when you multiply 2 vectors in a cross product, you end up with a third vector, and that third vector will always be perpendicular to both of the vectors you started with. So right here, this vector equation right here, vector A times, or the cross product of B is going to be equal to vector C. And you multiply some numbers to get the magnitude, but to get the direction, you've got to use your right hand. You get 2 choices here. You could do it this way, you can do it that way. But here's what you're going to do. In the first picture, point your fingers in the direction of the first vector. So if you just take your hand and point them in the direction of A, then you want to curl your fingers in the direction of the second vector. So there's B, and I've curled my fingers downward at a right angle. And then vector C would point up a right angle from that. All right. So fingers in the direction of the first vector, curl in the direction of the second vector, thumb points the direction of the result, vector C. All right. Here's plan B over here. I don't like this way as much, but some people like it, like to think about it this way. You hold your fingers in that weird little 3-dimensional finger gun thing, and you want to point your finger, your index finger, in the direction of the first vector, your middle finger in the direction of the second vector, and then the thumb would indicate the direction of the resulting cross product. All right. Either way works. I'll probably stick with the first way, but if you're used to the second way, that's fine too. Here's a good example of where you might use that. For example, if I have a moving charge, right there is some amount of charge. They've labeled it Q. It could be 2 coulombs, could be 2 microcoulombs, whatever. Could be an electron, could be a proton. If I shoot a charged particle into a magnetic field, right there, I'm moving with some velocity v. So there's a charged particle that's moving. But these X's represent a magnetic field into the screen. Now, remember how all this happens in 3 dimensions. It gets a little bit tricky to draw 3 dimensions on a 2-dimensional piece of paper. So one convention that we use here is if something's going into the board, we draw an X, and if it's coming out of the board at us, we draw a little dot. If you think about an arrow, if you look at the front of the arrow, you'd see the point the tip of the arrow, and it would be a little dot coming at you. Whereas if the arrow were moving away from you, you'd see the feathers on the back, or the fletchings of the arrow. So there we draw that little X to look like the feathers of an arrow going away from us into the screen. And that's just kind of a standard convention that helps draw pictures in 3 dimensions. All right, but once we've got that, then this charged particle moving to the right in a magnetic field that's into the board will experience an upward force. The formula is right here. F equals QV cross B. I'm taking these 2 vectors, the velocity vector and the magnetic field vector, doing a cross product, and then multiplying that by the charge. That's a scalar, not just a dumb old number, right? Not a vector. And that gives me the magnitude of the force. And I'd use the right-hand rule to get the direction of the force. All right. Over here, you remember that the cross product can be written VB sine theta. First vector, second vector, sine of the angle between the first and second vector. All right. So that's the formula. You want to know how much force is on that moving charge. You just multiply it and you get the magnitude. To get the direction, I'm going to put my fingers in the direction of the first vector. That's vector V. So I've got my fingers pointed to the right. I need to curl my fingers in the direction of the magnetic field. So curl them into the board, and my thumb points up. That particle would have a upward force on it. And as it moves to the right, it will experience an upward force. It's going to change its direction, and it's going to move up in a semicircle. If you don't go out of the magnetic field, it will go in a complete circle, and it will just be trapped in a circular path right there. All right, so that's kind of neat. Right here are some of these just to kind of practice with. So take your right hand and do these with me. I'm looking at the first one here, A. You can see that the velocity is down, so I need to put my fingers pointing down towards the floor. The magnetic field, I see a bunch of dots. Those are arrows coming at me, so I need to rotate my hand until I can curl my fingers pointing towards me, and that makes my thumb point off to the left. Okay, so that's what we've got right there. This particle moving downward through an outward pointing field is going to experience a force to the left, and its path will curve off like that. Here's the second one. Do this one with me too. I'm going to put my fingers pointing up in the direction of V. I've got to rotate my hand so that I can curl my fingers in the direction of B, and that means that my thumb points into the board. That particle would experience a force that would move that thing away from us into the board. Here's number C. Point your fingers to the right, curl them into the board, you get thumb up. All right, so there's an upward force right there. Its path would go like that. That's like the one we saw a minute ago. D is interesting. Remember that QVB sine theta? The angle between V and B is 180 degrees. The sine of 180 degrees is 0. This particle doesn't experience any force because the angle is either parallel or anti-parallel, moving in the opposite direction. When they're moving in the same thing, you don't get a net force. So this guy would just stream along like nothing was happening. Okay, so play with those and get used to that right-hand rule thing. We've got a whole bunch of it this time, so you'll need some practice with that. I got 2 little problems here, and then we'll be done with this video. Any kind of questions you have, bring them to our virtual class or a real class or whatever we get to have in the future. Right here in this one, I've got an electron that's moving at 4 times 10 to the 4,000 meters per second in a 1.25 Tesla magnetic field. It experiences a magnetic force of 1.4 times 10 to the negative 16 newtons. What angle does it make with the magnetic field? So here's one where we do need the sine theta part. It just doesn't turn into a 1. They're giving us a number. All right. But I do have a charged particle moving in a magnetic field. That's going to put a force on it. I know the force. I've gone ahead and gotten all the numbers here that are involved. They gave me 4,000 meters per second. I put that down. They gave me 1.25 Tesla. Tesla is the magnetic field, so I put B equals 1.25 T. Angle is what we're looking for. What angle does it make? And then they didn't give us this in the problem. Over here, see how I need the Q? They told me it's an electron. So I need to go look up the charge of the electron, which is 1.6 times 10 to the negative 16 coulombs. That's the right number? I thought it was 19. I don't have another tab here, but I didn't multiply it out, so it doesn't matter too much. Let's find out real quick. Charge electron. I think I hit a wrong button here. Yeah, negative 19. All right, so that's the type of 1.602 times 10 to the negative 19 should be that number right there. 1,000 apologies. So that number's, I think I put 1616 or something. That should be a 9 right there. Anyway, here's the force, the magnetic force on that thing, equal to QVB sine theta. We're looking for theta. So all I have to do is divide by QVB, and that would get me down here to the second line. I want to get rid of the sine, so I need to do an arc sine of all this stuff on the left is equal to theta. When I put the numbers in there, preferably the right ones, not this one, then that would give me theta. And in this case, I get about a 10-degree angle right there between those. All right. They do say there's two answers. What would the other answer be? Well, it'd be a 10-degree angle coming over this way. So, if that particle were moving kind of like that, I would have that amount of force. And I didn't put the force in the list. I should have done that. This number. All right. But 10 degree either way would do that. All right. Here's the last one, I promise. A cosmic ray electron moves at 7.5 times 10 to the 6 meters per second, 7.5 million meters per second, perpendicular to Earth's magnetic field. So this is a charged particle that's coming into Earth's magnetic field. This thing could actually hurt us. This is a fast electron. It's got a lot of energy, and it could do some damage if it were to hit us, some cellular damage, cause a mutation, cause cancer kind of damage. All right. The field strength 1 times 10 to the negative 5th Tesla. I think it was something 3 times 10 to the negative 5th in the thing, but that's going to vary depending on where you are on the Earth. So what is the radius of the circular path that the electron follows? So I've got my numbers over here. Looks like I copy pasted that. So again, that should be negative 19 instead of negative 16. But here's what happens. I've got that charged particle moving like this, and I put my fingers in the direction of V, curl in the direction of B. I've got an upward force there. So it experiences an upward force, and that's going to make it curve off like that. And then I could do it again. I say, well, here's the particle at a second time, and I put my fingers in the direction of V. Point your fingers up, curl them into the board. My finger points to the left. So now the force goes that way and curls it around. And here's the charged particle at a third time. It's moving to the left, and I curl my fingers into the board. My thumb points down. See how all of those point toward a central spot right there? This is a centrifugal force. That's going to cause circular motion. And if I come over here and say that magnetic force is the centrifugal force right there, then I can set these two equal to each other. They wanted the radius of the circular path. So I just solved this R. In this case, they didn't give me an angle, so I'm assuming that it's 90 degrees. But that's a pretty safe assumption with this one. In general, if they don't give you an angle, just assume it's 90. Oh, actually, it does give. It says perpendicular, right? So it is written in there. But even if it weren't, I would probably assume that it was. I want to solve this for R. So what we've done here is to do a swappy thing with R on the bottom here and QVB there. Just multiply both sides by R, divide both sides by QVB, and you'll end up with that next to last line there. The number that you get is about 4.27 meters right there. And potentially Earth's magnetic field could just trap that thing moving in a circle with radius of 4 meters, and it never gets down to Earth. Earth's magnetic field protects us in this way, and it keeps a bunch of space radiation away from us, which is kind of nice. Okay, I'll have a couple more videos that we'll watch, but this is the first of them. Any questions you have, anything you want to talk about, just make a little note. Get started on the homework and see how far you can get and bring those questions in, or email me, or whatever I can do to help. And thank you for your time. Have a good day.